Okay, so basically before we start the lecture, I'm going to talk about the mistake I did last week. I uploaded recording for the lecture number 1 in the week number 2. I will shift this one back, and this one is going to be the lecture 2 recording. Also today, I posted some videos here, which are sections of today's lecture. Once again, as I told you, these lectures are going to be something maximum 10 to 12 minutes. Minimum 4 minutes, because I know that most of the students hate to watch long videos. So this will be specific. It's just part of this video. Can tell you about of the lecture. Sorry, can tell you something like the melting characteristics for the elements, the physical properties of the material, the hardness, the mass diffusion, and the engineering materials. I left the first part, but I'm going to do it today, and it's going to be a part of today's lecture recording. We still have 2 minutes to go for that, and actually for these videos you can find them simply by going to the learning material folder and you go to the second week face-to-face teaching, and you can find a folder for the pre-lecture material. So this is not going to be posted too early. It's posted for the time it's going to be suitable for you to watch it on your way to the lecture. So at least you're going to have, you'll understand what we're going to have in the lecture, and we're going to spend more of the time to ask questions rather than try to understand what I'm saying. So if you had a look for the lecture notes for today, mainly lecture number 2 will cover the following topics: the mechanical properties of the materials, the physical properties of the materials, and we're going to talk once again about the engineering materials. That's something we covered officially last week. So we still have another 1 minute to go. Did you have any technical problem to reach the videos? Yeah, I made it online because what's happened that some of the browsers, and especially the Firefox, if you try to click on the video which is uploaded to UTS Online, it will try to download it to your computer or your device before it's going to play it. So I prefer to keep the videos on the YouTube. It's much better to go to the YouTube, which is going to be much lighter for your phone to play the videos. So let's start with today's video, the lecture. Okay, as we mentioned earlier, that today's lecture is going to cover the following topics: the mechanical properties of the materials, like the stress-strain relationship, the hardness of the material, the effect of the temperature of the properties. And on each one, we're going to talk how this will affect on the manufacturing process. Also, we're going to talk about the physical properties of the materials, like the volumetric and the melting properties, the thermal properties, and the mass diffusion. And then we're going to go once again to talk about the metals and their alloys, the ceramics, the polymers, and the composites, and a little bit more details. So I believe that, before we go into this one, I believe that most of you know what the stress and the strain is, right? You know what the stress is and what the strain is? Yes? Okay. And you know there's a relationship between them. And definitely you know the terms of the plastic and elastic. So we're going to show you today that as long as we're going to add some stress to the material, we're going to have a change in the length, okay, proportional to the original length, and that's what we call the strain. Actually, stress is just adding the force to a certain area, and this will change the properties like the dimensions, and the change in the dimensions, what they call it, the proportional change in the dimension will be called the strain. Usually, most of the materials have some elastic range And if they're going to pass a certain stress value, they're going to go to the plastic range. So elastic means that at the minute we're going to remove the load, the shape will retain back to the original shape. If I'm going to pass the plastic region, every force I'm going to add is going to cause a permanent deformation to the material. And that's actually the main important thing we have in the manufacturing. So the mechanical properties of the materials determine the metal behavior when they're going to be subjected to mechanical stresses. And these are the elastic modulus, the ductility, the hardness, and other various measures of the strength. You may never went through this one yet, but for the elastic modulus is what the material property to go to a certain deformation and retain back to original shape. For the ductility is the ability to take some stresses without being fractured. This is a simple definition for that. Now, for example, the piece of wood is going to be non-ductile material. It's going to be almost brittle, or the brick. Okay, the brick actually, when you're going to add the force, is not going to be bended and retained back to the original shape. It doesn't have ductility. It's a brittle material. It's going to break up. While the, for example, the iron, okay, the steel bar, you can bend it to a certain level. When you're going to relieve the force, it's going to retain back to the original position. So it's ductile material. And usually in manufacturing, we're looking for the ductile material if you want to do some machining on it or deformation. The hardness is how hard the material to take these stresses. And we're going to talk about the other various measures for the strength. We have three types of the static stresses to which the material can be subjected to. Okay, now you know what the term of the tensile, what the term of the compressor, and what the term of the shear. That's a specimen. If I'm going to compress it from both directions, it's going to be under the compressive load. If I'm going to pull the forces to the opposite directions, it's going to be under the tensile force. If I'm going to twist it, or if I'm going to add a force to try to break it in a certain plane, it's going to be called the shear stress. So tensile is stretching the material, and the compressive is squeezing the material, while the shear is causing the adjacent portion of the material to slide against each other. It's something like when you cut a paper using the scissor. Actually, we do shear cutting on that because we're going to have this slide, which is going to leave each other adjacently. The stress-strain curve is a basic relationship that is going to be described the mechanical properties of all three types of the stresses. So first we start with the tensile test. We have machine downstairs, and I hope I can take you one day to show you how the tensile test is happening down there. You are going to have some labs starting from next week at B4, right? Okay, I'll try to get a permission from the school to show you how the thing is happening and how we can simply make the stress strain diagram. So that's how the tensile test is happening. We have a specimen which have the original height and the original diameter or the cross-sectional area. Now what happens if I get to add some forces, try to stretch this part? What will happen to the height, which is the length of the specimen? It's going to go longer, right? So if it's going to be longer, well, we have a constant volume. So what will happen to the cross-sectional area? You know that the volume of the cylinder is equal to the cross-sectional area multiplied by the height, right? So HO multiplied by the AO should be equal to the volume. The volume is going to be constant. If the H is going to be higher, that means that the area should be getting smaller. So that's what will happen in after the tensile test. The area getting smaller, the height is going to be higher. We keep adding forces in a certain specimen. That's a specimen we're using for the tensile load. Different material, making the same specimen, put it on the machine, have supporting column, and add the forces, and we're going to have the tensile specimen to get longer with a smaller cross-section area. So is that going to continue forever, or we are going to reach a certain force which is going to cause the nicking to appear? Then we're going to have the fracture. That's obvious. So we are going to check what will be the final load, final length, after putting back the specimen parts together. The length is going to be measured between the gauge mark we have on the specimen. We know what the original length is. Then simply we can check what the stress we had for this material at a certain time is going to be equal to the force we applied divided by the original area. This will be the stress we add on this part. For the strain, which we said is a proportional elongation of the material, simply the strain is going to be equal to the final length, or the any length during the process, divided by minus the original length divided by the original length. So what will be the unit in this case here? The force usually is going to be in Newton divided by the area, which is in square meter. So the stress unit is going to be is Pascal. What will be the units for the strain? Unitless, okay? Because it's meter minus meter divided by meter, and the strain is going to be unitless. Simply we can sketch that by taking the multiple value of the forces divided by the multiple value of the areas, and we can find the value of the stresses. At the same time, we can simply, each time, the length, the instantaneous length minus the original length divided by the original length, we can find the value of the strain. So what's happening is that the elongation will start to occur when we have still in the elastic region. If I'm going to remove the force at any point before we finish and reaching the Y point, which is the yield point, the length of the part will retain to the original length. If I'm going to pass the yield point, every deformation will occur after this stress is going to be permanent. And we are going to call that the plastic region. At the maximum load, we are going to start to have the nicking. And after that, the nicking will accelerate, the stress will be less, and then we're going to have the fracture to occur. Anything below the plastic region is going to be simply use the Hooke's law to determine what the value of the strain according to the value of the stress by knowing the value of the E. Okay, but this should go up. Just give me 1 second. That's strange. Okay, so this is the typical simplified shape, but the actual one, it should be the true stress strain diagram, which is going to be the stress in this case is going to be the force divided by the actual instantaneous area. And for the elongation strain is going to be the ln natural logarithm of the length, instantaneous length, divided by the original length of the material. So the ductility definition is, and highlight this one because this can be questioned in the final exam. And actually, you have this question at the end of the chapter question in the book I gave you. So the ductility definition is the ability of the material to plastically strain without having a fracture. That means the ductile material is going to have longer area in the plastic region. Longer line in the plastic region is the ductile material. If the material is going to be fractured at the beginning, we are going to call it the ductile, the opposite ductile. I just mentioned that earlier. Anyway, the brittle material. So to define that, the EL is going to be simply equal to the length LF, which is specimen length at the fracture measured at the distance between the two gauge marks, minus the original length divided by the original length. The true stress will increase continuously in the plastic region until we're going to have the nicking at the top. And it means that the metal is going to become stronger as the strain is going to be increasing. And this is what we call the strain hardening. So we have two important definitions in this page. The first one is the ductility definition, the ability of the material to plastically strain without having a fracture. And the other term is the strain hardening, which is the increasing of the metal strength as long as you increase the strain. And that's actually what we have in the case of the rolling and the case of the forging. Okay, so just highlight these two definitions, ductility and the strain hardening. The true stress strain curve plotted in the log-log scale is going to show as following. So in this case, we don't use the hook slope. Instead of that, the law we're going to use is going to be the following. The stress is equal to the constant multiplied by the mu, which is strain out to power n. To define that, the n is the slope of the curve. And the K is the strength coefficient, which is going to be different from one metal to another. If I'm going to have a material which is going to be called perfectly elastic, that means it's never going to reach a yield point. What will be the example for a perfectly elastic material? The material that you are going to be simply add the force on it is always going to be in the elastic range, but when it's going to pass the yield point, it's going to fracture. That means it's going to be a brittle material. So that's what we talked about. For example, the ceramic is a perfectly elastic material. It cannot go to any plastic deformation. When it's going to reach the yield point, it's going to fracture directly. The elastic and the perfectly plastic material, in this case, the metal will behave like this when it's going to be sufficiently high temperature, and simply you can shape it as you would like to have it. Now, if I'm going to increase the temperature of the steel, and then I'll try to bend it, when it's going to reach a yield point, it's going to be bent using the same force without any resistance, simply because I increase the temperature beyond what we call the recrystallization temperature, which we are going to define soon. The other type is going to be elastic and strain hardening. And in this case, the value of the K is going to be more than the yield point, and the value of the slope is going to be more than 0. And this will be most of the ductile materials is going to be behave that when it's going to be cold work, like the metal sheet when you try to bend it. It's always going to be elastic and strain hardening material. To find more properties, we can do an opposite to the tensile test, which is the compression test. Are we going to have any fracture in the compression test? Now, the fracture happening in the tensile test because we were increasing the length, reducing the cross-sectional area, we had the nicking to appear, then at a certain value of the nicking, it became too small, we had the fracture. Now, the opposite way, I'm compressing the thing. So no fracture is going to be happen. And theoretically, we may have the flattening for the material, but in actual life, we're not going to have the full flattening of the material. So the same specimen, well, actually, it's not the same specimen because the specimen we had for the tensile test have threads from both ends to hold the part while I do the tensile. But for the case of the compression test, it should be flat, so we can simply compress it between two dies. So what we have is the same thing, the original height and the original cross-sectional area. We're going to add the force, which try to compress the part. Now, the same theory, we have the same volume to be constant. The height is going to be reduced, So in this case, the cross-sectional area will be an increase instead of decreasing like what we had in the tensile load. Okay, so the part is going to be shorter, the cross-sectional area is going to be bigger. So the device we're going to have is almost similar, but as I said once again, we're not going to have the thread on the specimen to pull it up, we're going to compress it down. So in this case, the stress is going to be negative because we're compressing the thing. So it's going to be always going to be equal to the force divided by the cross-sectional area. And for the strain, and actually that's strange. Why do we have to show this one down here? Okay, so, and the strain will remain the same. So it's going to be negative, but we're going to consider it as a positive value because there's no percentage of the negative height changes. And in this case, as you can see that the stress strain diagram is going to go up because we're not going to have any fracture. We're supposed to have a flattening for the material itself. So as the specimen compressed, the height is going to be reduced and the cross-section area is going to be increased, and the stress is going to always equal to negative of the force because it's making a compression divided by the original cross-section area. And since the height is going to be reduced during the compression, the value of the E is going to be negative, and the negative sign is going to be always ignored when the expression of the compression strain diagram. So the shape is going to be different from the tensile test because the cross-section is going to be actually increasing. And that means that each time we're going to add the force, so if I get to have a brittle material, I cannot do either the tensile test, neither the compression test, right? Because in both cases, in the tensile test, it's going to break up at the minute it's going to reach the yield point. If I'm going to compress, it's always going to be smashed at the minute I'm going to reach the yield point. So we have a different method to test for the brittle materials. So the hard brittle materials, like the ceramic, for example, they're going to possess some elasticity, but they don't have, or they have a little bit of the plasticity. They will never change the shape due to the adding of the stresses. So we have to do a conventional test. A tensile test cannot be simply applied. We have to add another type of test. So the brittle materials do not flex. It's going to break up at the minute you try to bend it, and they deform elastically until they're going to fracture. So usually the failure is going to be occurs because of the tensile strength of the outer fibers of the specimen are going to be exceeded. Now this is my part. When I try to bend it, the fracture is going to be occur usually at the end, and then it's going to go through all the material because the outer fiber, as we said once again, they're going to exceed the tensile strength for this material. So the failure type is called the cleavage, which is common with the ceramic and the metal at low temperatures, in which the separation rather than the slip will occur along a certain crystallographic plane. So if I would like to form the ceramic, what will be the solution to do that? That's away from the slide. But you can have the answer in this page. If I would like to make a permanent deformation for a ceramic part, What will be the solution to do that? How to form the glass. Have you seen videos for that? Yeah. They heating it up. Yeah. Above the crystallization temperature, start to have some melting, then you can simply do the bending and it's going to be permanent. So the answer is here that said that the cleavage, which is the failure, is always going to be at low temperatures. So simply just increase the temperature, then you can do any type of deformation in the plastic region. So the test we use for the brittle materials is going to be called the bending test. That's my specimen. Put the load in the middle. I know what the height, what the width, and then simply this will be the initial loading. And I'm going to have some certain changes. I don't have to go beyond the strength of the material we're going to have to get the fracture. And then I'm going to check the compression at the top and the tension at the bottom. The other type is what we call the shear properties. So we said that the shear properties is sliding on the material and having the cutting. So that's what will happen. I can add forces on opposite direction. This will be the original cross-sectional area. Again, to have a certain sliding in the material, which is the shear strain. Then simply, I can calculate what the value of the shear stress of this part. By same thing, the force divided by, in this case, not the cross-sectional area, but the shear area. So the application of the stress is going to be opposite in directions on either side of the thin elements, and we're going to have the shear stress and the shear strain. Shear stress, the force divided by the cross-sectional shear area. And for the shear strain, which is going to carry the gamma, is going to be equal to the deformation we're going to have here divided by the height of the specimen after the deformation. Of course, the slide you have is better than this one because I don't know why I cannot remove the bar from here. I'll try to do this one later. Also, we have another term which is called the torsion stress strain diagram. Now, the torsion is different from the shear because we're twisting the part. So the typical shear strain curve is going to be shown as following. Okay, this will be same thing, shear strain against the shear stress is going to continue until we're going to have the fracture. And now, once again, that's what we have in case if we're going to use the scissor more than the knife. And that usually is used in the cutting of the metals, and we're going to talk about the shear cutting in the future. And that's why we have to understand how to reduce the value of the yield point to have easier cut for the metal using the shear cutting machine. Now we can see here that the elastic region, in the case of the shear elasticity, is not going to use the E, which is the modulus of elasticity, like in the case of the tensile stress. In this case, we have the value of the G, which is the shear modulus, is different. The hardness, and actually I start to make videos for this lecture from this section. The hardness of the material is its resistance to have a permanent indentions. So that means if I'm going to have a soft material, that means simply I can do a permanent deformation for it with minimum force. The harder material like the steel is going to be harder material because it has more hardness, so it's going to have more resistance to have the permanent indentations. So the good hardness generally means the material is going to be resistant to scratching and wear, and most tooling used in manufacturing must have a hard for scratch and wear resistance. We have a hardness test simply to assessing what the hardness of the material we are going to use. And this is divided into two types, and that's why we have two scales for the hardness of the material. The first one, which is the most common one, is called the Brinell hardness test. The other type is called the Rickwell hardness test. Now, the principles are the same, but the which they are using to test the metal is going to be different. Brunel used a ball. Know what the diameter of this ball? Simply, he's going to press it against the surface of the specimen to a certain value of load. For example, we start with 500, 1,500, or 3,000 kilogram. Remove the ball. Check what will be the diameter of the indentation we're going to have on the surface. On the Rockwell hardness test, instead of using the ball shape, he's using the wedge shape. So we're going to press the wedge, and we're going to know what will be the initial indentation and the final indentation using the certain force, and we're going to check what the value of the D. How we can simply change the ductility of the material, as we mentioned earlier. We said that for the ceramic, if I would like to change its hardness or change its to make it ductile rather than the brittle, we simply increase the temperature. So this is an example for how the temperature is going to affect on the properties of the material. So for the tensile strength, is going to be lower as long as we're going to have a higher temperature. The yield strength will go lower as long as we're going to have higher temperature, while the ductility is going to be increasing at higher temperature. Now, what will that give you? If simply going to have a lower yield strength at higher temperature, what will that help us to do? With? Yeah, bending the material with? Now, you heated the things. Okay, so you're actually going to use less force to make the bending to occur, the permanent bending to occur. So that's what we call the hot hardness, by simply increasing the ability of the material to retain the hardness at elevated temperature. So even the ceramic, as you can see here, is going to have a lower hardness at higher temperature. Now, the term of the recrystallization temperature has been mentioned earlier. If the metal is going to be increased to a sufficiently high temperature to be undeformed, then the strain hardening does not occur. Now, we said that the strain hardening is the increasing of the strength of the material by increasing the strain of the material. Instead of that, simply we are going to have a new grains going to be formed, are going to be free of the strain, and the metal is going to be recrystallized once again. So the metal is going to behave perfectly plastic material, which means that the value of the N for the slope is going to be equal to 0. Now you remember the stress is equal to K multiplied by the strain up to power N. So if the N is going to be equal to 0, that means that the stress is going to be equal to the K. And that will make it what we call a perfectly plastic material. We're going to have a straight line for the range of the plasticity. The crystallization temperature, we know that the crystallization is going to take some time to occur, and the crystallization temperature is going to be specified as a temperature which the new grains are going to be formed in about 1 hour. And the value of this temperature usually is going to be half of the melting temperature of any metal. Usually the crystallization temperature is used in the case of the heat treatment. Now to explain that to you once again, that if I'm going to bend something, I'm going to have stress on one side, compression on the other side. So this crystalline shape of the material is going to be changed. So if I would like to recrystallize the shape to have more homogeneous crystallization shape, I'm going to heat it to half of the melting temperature and release temperature within 1 hour. So the application of the recrystallization in the manufacturing, heating of the metal to its recrystallization temperature prior to the deformation will allow a greater amount of the straining, and thus we are going to have a lower force and power to be used. And the forming of the metal at the temperature above recrystallization temperature is going to be called the hot working. Anything below 0.5, below the crystallization temperature, is going to be called the cold working. Now, rather than the mechanical properties of the materials, we have some physical properties of the materials. Like, there are the properties of the materials that like the behavior of the metals and the response to the physical forces, other than the mechanical forces, like the volume, the thermal, the electrical, and the electrochemical properties. So what did we mention about the volumetric properties of the material? What will happen to the material volume when you are going to increase the temperature? We said something about the expansion and contraction. Okay. And the thermal, what are the thermal properties of the material? Conducting and non-conducting for the thermal. And for the electricity, same thing, conducting material and non-conducting material. And for the electrochemical, if they're going to be simply dissolving or non-dissolving materials. So they are very important. These physical properties are very important in manufacturing because the physical properties are often going to influence the process of the performance. For example, in the machining, the thermal properties of the work material determine the cutting temperature, which is going to affect the tool life. In the microelectronics, the electrical properties of the silicon are the basis of the semiconductor manufacturing. So let's talk first about the volumetric and the melting properties for the materials. The properties are related to the volume of the solids, as we mentioned earlier, and how these properties are going to be affected by the temperature, like what will happen in the density, what are the thermal expansion and the melting point. So what will happen to the density when you are going to increase the temperature? The mass is constant. Say constant, not the same. The mass is constant. The volume expanded. So what's happened to the density? Decreases. So the density, as we define it, is the mass per unit volume. So how many grams we have per every cubic meters? Or how many kilograms we have in cubic meters? The specific gravity is the density of the material relative to the density of the water. Thus is going to be the ratio with no units. For example, if the density of the steel is 7,800 kilogram per cubic meter, what will be its specific gravity? 7.8. Simply divide the 7,800 by the 1,000, which is the density of the water. So the specific gravity is going to be 7.8. So the density is important in manufacturing, in consideration of the material selection for a given application, but it may be not only property of the interest we may have. The strength is also may be important, and we have the two properties are going to be often related to the strength to weight ratio, which is the tensile strength divided by the density. And this is very important actually in the manufacturing process, because if you would like to make an airplane, you cannot use a very strong material because the strength to weight ratio is going to be too high, and thus is not going to fly the aircraft unless you're going to use too much energy to do that. The same thing for the car. So the point is how to reduce the energy to move the car. So you have to choose a material which is going to have a good strength to weight ratio for it. The thermal properties are the properties that the temperature determines the thermal energy level of the atoms, leading to the change in the material. For example, we're talking about the thermal expansion, the melting, and the heat diffusion. Now, the thermal expansion is how the heat is going to expand the material when it's going to increase. For the melting is the temperature when the material is going to change the phase. That's mean from solid is going to change to liquid. And the heat of fusion, we're going to talk about this one next. So the additional thermal properties we can have is the specific heat for the material, the thermal conductivity, and these properties are related to the storage and the flow of the heat within the substance. So first about the thermal expansion, and actually, oh, by the way, have you checked the UTS online for the following? On UTS online, every week, we submit these examples, the calculation examples. Okay, so for example, click that. You have to add the password, which is UTS, I think. Yeah, UTS caps, and you will have some questions, calculation questions. Some of these calculation questions is going to be question in the final exam and is going to carry 10% to 15% of the total mark. So you may have something related, yeah, because actually this is about the melting temperature and determining the properties of the phase. Yeah, it's very simple calculation. It's a straightforward one. And actually, you have to practice this one and double check it with the answers you have here. This will be very helpful for you to get extra marks in the final exam. Okay, so for the thermal expansion, as we mentioned earlier, that the density is going to be decreased as the temperature is going to be increasing, simply because your volume is going to be increases, while the mass is going to be the same. The effect of the temperature of the density is going to be called the thermal expansion and measured as a coefficient of the thermal expansion alpha. So the coefficient of the thermal expansion is the change in the length of per degree of the temperature we are going to have. So the unit is going to be how many millimeters we are going to increase the length to the original length per every centigrade of the temperature again to add. So the alpha is going to be calculated by the final length minus the original length divided by the original length multiplied by the temperature difference. Okay, so it's millimeter divided by millimeter multiplied by centigrade. The thermal expansion is very useful, especially in the process of what we call the shrink fit. So if I would like to get a bigger diameter shaft in a smaller diameter hole, the best thing is to heat it up. It's going to be expanded. Then I can to insert it with lower force, contract, and we are going to have the tighten up of the parts together. Thermal expansion can be a problem in the case of the heat treatment and the welding due to the thermal stresses that develop a material during these processes. Now, a very important thing, because this will be introduction for what we call the solidification manufacturing process, which is the casting process we're going to talk about in 2 weeks. So the melting characteristics for the elements is very important. If I get to have a pure element, for example, I got a cube of just copper, and I'm going to expose it to a heat. It's a pure copper. So all the part is going to be melt at the same melting point because it's a pure copper, right? It's have only one melting point, and what we're going to call the TM. So in a pure element, the melting point is the temperature which it transforms from the solid to the liquid state. The freezing point is the opposite one. Okay, so it's the temperature that the liquid transforms from the liquid to the solid state. The heat energy definition is the amount of the energy required to accomplish the transformation from the solid to the liquid. Okay, now we have how many definitions in this page. The melting point is very simple, the temperature required to transform the metal from solid to liquid. Freezing, change from liquid to solid. And the heat energy, the heat of now, if I don't have a pure metal, that means I have at least mixture of two metals, I will call it an alloy, which is a mixture of two metals. Now in this case, I'm going to have two melting temperatures instead of one melting temperature. So what will happen in this case is that one of the metals, which have the lower melting temperature, is going to be changed from the solid state to the liquid state, while the other one will remain as a solid state. So I'm going to have a mixture of the solid and liquid metals at the same time. So the melting will begin at the temperature which is going to be called the solidus and continuous as the temperature increase until we're going to convert in the completely liquid to a temperature called the liquidus. So the temperature which is going to melt the lower temperature, melting temperature metals is called the solidus. And then we're going to have a mixture of both. And when both metals are going to be melted, this temperature is going to be called the liquidus. So the solidus and the liquidus is going to be shown in the next diagram. So between the two temperatures, the alloy mixture is going to be a mixture of the solid and the molten metals at the same time. The only exception we have is what we call the eutectic alloys, which is going to be melt and freeze at the single temperature. So that's what's happened. These are the temperature. We have I need to remove the bar. I don't know how. Okay, so this is my alloy, which consists of the nickel and the copper. As I'm going to increase the percentage of the nickel in the alloy up to 100%, you can see that in 100%, I'm going to have one melting point. It's a pure metal. 0% for the nickel, 100% for the copper, I'm going to have one melting point. As long as I'm going to increase the percentage of the nickel in the alloy, I'm going to have a different status in this case. Now, in this case, I'm going to have a line at the bottom, which is going to be called the solidus. So the solidus is the temperature where the lower melting temperature metal is going to be melted first. And in this state, I'm going to have a mixture of the liquid and the solid of the two metals. Until I'm going to reach the higher temperature, which is going to be the liquidus, where both are going to be changed into a liquid solution. In the case of the non-crystalline materials, like the glasses, for example, we are going to have, instead of the sudden change in the melting, like what we have in the case of the solid pure metal, or in the case of the solid alloys. Okay, now this is what's happening in the pure solid metals. For example, I have an aluminum, pure aluminum. I increase the temperature. It was solid, and suddenly it's going to be changed into a liquid. In the case of as we said, the nickel and the copper, we're going to have a gradual changes because we are going to have the solidus mixture and the liquid and the solid alloy mixture in the middle. This is solidus, where the copper is going to be melted first, and the final stage where both are going to be melted. So it's going to be a gradual. But in the case of the glass, it's always going to be a gradual transition for the state from the solid to the liquid material. The solid material are going to be gradually going to be softened first, and that's where we can simply shape the glass in the softened state. And then as the temperature is going to be increased, finally it's going to become a liquid at the melting point. And during the softening, the material has a consistency of the increasing of the plasticity, and as it's going to be gets closer to the melting point. How we can use the melting in manufacturing? The most important process is going to be the metal casting. If I would like to shape, for example, the engine block, I can not simply, I can do the machining actually, but it's going to be quite expensive, and I'm going to have too many losses in this case. And the properties are going to be the same. So doing the metal casting by simply melting the material and fill the cavity in the casting mold, as we mentioned last week, leave it to solidify again to have the finished part. Also, it's very important in the plastic molding, again, to melt the plastic, inject it to the mold, and leave it to solidify. And in the case of the sintering of the powdered metals, like the example we gave last week for the compressed powder to make the key in your pocket. So if you're not going to do the internal melting of the material, it's not going to be hard enough to be used. So other terms like the specific heat, the volumetric specific heat, the thermal conductivity, and the thermal diffusivity is going to be given next. Specific heat is the quantity of the heat energy required to increase the temperature of the unit mass of the material by 1 degree. For example, how many degree I would like to change, to add to increase the temperature of small cubic shape of the metal by 1 degree. Is going to be called the specific heat. And simply it's going to be calculated by using the equation. The H, specific heat, is equal to the C multiplied by the W multiplied by the delta T. H is the amount of the heat energy, C is specific heat of the material, W is the weight, and the delta T is the change in the temperature we are going to have. The volumetric specific heat is the quantity of the heat energy required to raise the temperature of the unit volume, so not the unit mass as that's what we had in the specific heat, by 1 degree. So in this case, it's going to be called the rho C, where the density of the multiplied by the specific heat value in this equation. The thermal conductivity is the capability of the material to transfer the heat by transferring the thermal energy within the material from molecules to molecule by purely thermal motions. And to determine what the thermal conductivity value is, we have to use the term of the coefficient of the thermal conductivity K. And once again, this is very important in the case if you are going to design, for example, a heat exchanger, or try to choose the material required in case if you are a mechatronic engineer to make the heat sink for the computer processor. The thermal diffusivity is the ratio of the thermal conductivity to the volumetric specific heat. Is going to be frequency encountered in the heat transfer analysis. I'm not going to change this one because simply you can see this one on the slides you have in front of you. Now, the thermal properties in manufacturing process, the heat generation is common in many processes. Now, if you're going to do the machining for the part, you're going to have direct contact between the cutting tool and the work part. We're going to have a fraction, so we're going to have increasing in the temperature, and that's why the thermal properties is always going to be important in this case. In some cases, the heat energy is going to be accomplished by the process like the heat treatment, the sintering of the powder metals and the ceramic. In other cases, the heat is going to be generated as a result of the process like the cold forming and the machining of the metals. For the mass diffusion is the movement of the atoms or the molecules within the materials across a boundary between the two materials in contact. Now, simply if you are going to have two materials going to be compressed together by a certain force, we're going to simply what we call the well, it's joining process, just compress them together to have the permanent joining. So what's happening is that after a certain time, you can see that the molecules of one material is going to be within the other to a certain depth. And that's what we call the mass diffusion. So the atoms are going to be continuously moving about due to thermal aggregation of the atoms in the materials, like in the case of the solid, liquid, or the gas. In the case of the liquid and the gases, where the level of the thermal aggregation is going to be high, it's going to be a free roaming movement. In the case of the metals, where the atomic motion is going to be facilitated by the vaccines we have, and other implications in the crystal structure, we're going to have a lower motion to occur. So this is just an example, and we're going to talk about, for example, the liquid state. Just imagine we are only going to use water, but each one have a different color. And you have a partition in the made of them, between them. If we're going to remove the partition, what's happening that the molecules is going to go on both directions, and we're going to have the mixtures. So this is a case of the mass diffusion, if we consider that the color is different materials. At the end, we're going to end up with a uniform mixture of A and B with a homogeneous shape. At the end, we're going to finish with the water have the same color all over the place. So that's what we have in the case of the mass diffusion. We have one concentration of the material A and 0 for the material B. When the process is going to start, again, to have a continuous, a curved line when the things start to mix up together. And we are going to end up by having the concentration of the material A and B is going to be 50% of each. So how can we use the mass diffusion in manufacturing? It's very important in the surface hardening treatment based on the diffusion and include the carburizing and the nitrizing. So if we're going to have a surface, we're going to be called a carbonized surface. Simply we impose the carbon on the surface of the steel, and we're going to have a carbon steel covered. Also, we have it in diffusion welding, where you use two joint of the component by simply pressing them together and allowing the diffusion to occur across the boundary to create the permanent bond. And diffusion is also used in the electronic manufacturing to alter the surface chemistry of the semiconductor chip by a very localized regions to create the circuit details. So I don't know where we can find the diffusion welding around you, but if you ever seen the frame of your car door, you will see there are some spots there, and this is actually the diffusion welding. You're just suppressing the two metals, and you passing current through. It's going to make a high temperature. So it's having that the molecules of both metals are going to be joined together, and that's why we have the melting to occur. Now we talk once again about the engineering materials, and that's something we covered earlier. So can you simply classify what are the engineering materials we have in manufacturing? You remember that? We said we have mainly three different types, which are the metals, ceramics, and polymers. Okay, so the metal important properties we should have in manufacturing are the high stiffness and strength, the toughness, the good electrical conductivity, and the good thermal conductivity. The forms of the metal in manufacturing, it can be a cast metal, it can be a wrought metal, and it can be a powdered metal. So the cast metal is starting form is going to be the casting. So simply I can bring the iron ore and the copper ore, mix them together, melt them again to make a cast shape. Or I can do the wrought metal where the metal is going to be worked. So it can be worked after the casting process. Like for example, I'm going to do the rolling to make the metal sheets. The powdered metals, where the starting form is going to be very small powder for conversion into a parts using the powder metrology techniques. Now, how to make the powder for the powder metrology? Simply, I can make any alloy or again melt any pure metal, and I'm going to spray it with air. It's going to be separated into small particles. Further, I can simply do the grinding for these metals to make it in a powder form. I can do the blending and the mixing to have the final mixture I would like to compress in the powder metrology process. So for the metals, it can be classified into a ferrous, non-ferrous, and superalloys. So we said that the ferrous metals are every metal which is going to be based on the iron, is going to contain an iron in them. The non-ferrous are all the other metals which does not contain the iron, and we have the superalloy which can be a mixture of both. So the ferrous metal based on iron, and engineering are alloys based on the iron and the carbon. And these alloys are divided into two major groups, which are the steel and the cast iron. We mentioned earlier that together they're going to simply going to concentrate as if 85% of the metal tonnage in the United States alone. So the first thing we are going to talk about is adding the carbon to the iron to make the steel. So we have the iron carbon phase diagram, which is going to be consist of the alpha value plus the ferrous up to 3 carbon, and how the thing is going to be changed. So we can see that we have alpha, we have gamma here, gamma plus L, and we have the liquid state. So at room temperature, the phase is going to be alpha. Okay, and it's called the ferrite, which is a BCC. Now, what's the BCC term is? Body central cube. If I'm going to increase the temperature up to 1912 degree, the ferrite transforms to a gamma. From alpha is going to go to the gamma. And in this case, it's going to be called the austenite. Now, just remember once again, the alpha is the ferrite. The gamma is the austenite, which is going to be, in this case, a face-centered cubic. As I'm going to increase the temperature to 1394 degree, I'm going to change it to a delta, which is going to be once again as a body-centered cubic. And the pure iron metal is going to be melted at 1539 degree. I'm going to have the total liquid at this state. For the steel, is an alloy of iron which contains something between 0.02% up to 2.11% of the carbon by the weight. That means for every 1 ton, we're going to have something about 20 grams up to 21 grams of carbon. And also, it may contain other alloying elements to improve the properties of the steel. The steel alloy can be grouped into 4 categories, which are the plain carbon steel, the low alloy steel, and the stainless steel, and the tool steels. That's the plain carbon steel, which is a carbon is going to be a principal alloying element with only a small amount of the other elements, like for example 0.5% of manganese is going to be normal. Strength of the plain carbon steel is going to be increased with the carbon content, but the ductility is going to be reduced. Okay. And the high carbon steel can be heat treated from the martinized, making the steel very hard and strong. And the low carbon steel can be is the one which having 0.2% only of the carbon. The medium carbon steel, which contains something between 0.2 and 0.5% of the carbon, and the high carbon steel, when we're going to have higher than 0.5% of carbon. The low alloy steels, it is an iron carbon alloys containing additional alloying elements beside the carbon. But in total, is going to be always less than 5% by weight of the total alloy weight. The mechanical property is going to be superior to the plain carbon steel for given applications. It's going to have high strength, hardness, hot hardness, wear resistance, and more tough. And the heat treatment is going to be often required to achieve those improved properties. The tool steel, which usually from the name is used to make the cutting tools, is a class of highly alloyed steels designed for the use in the industrial cutting tools, dies, and molds. And to perform these applications, they must have a high strength, hardness, hot resistance, wear resistance, and toughness under impact. And these are usually going to be heat treated. The stainless steel, which is very common material, highly alloyed steel designed for the corrosion resistance. actually stainless, is not going to be corroded. Uh, Corrosion resistance is going to have high strength and ductility, but is going to be significantly more expensive than the plain carbon steel or low alloy steels, and are difficult to work in manufacturing. Now, why is going to be more difficult to work in manufacturing? Because of the high strength. Okay, so it's going to affect on the power you're going to use in manufacturing. The principal alloying element is going to be the chromium, and usually it's going to be greater than 15% in weight. The nickel also is going to be applying as another alloying ingredient in a certain stainless steel to increase the corrosion protection. The carbon is used to strengthen the hardness of the stainless steel, but high carbon steel simply going to reduce the corrosion protection because they corroded because they have carbon in it. Since the chromium carbide forms to reduce the available free chromium in the mixture. So classified according to the predominant phase presence of the ambient temperature, we have the austenitic stainless steel, where it's going to be a typical composition is going to be 18% of the chromium and 8% of the nickel. And for the ferritic stainless steel, it's going to have 15 to 20% of the chromium, low carbon, and no nickel in it. And the multinastic stainless steel is going to be as much as 18% carbon, no nickel, 18% chromium, no nickel, and higher carbon content than the ferritic stainless steel. Now, the cast iron is very common material in manufacturing because it's very easy to manufacture. Simply, the content is going to be not that important as the stainless steel. We don't care about the corrosion, but it have a good weight to strength to weight ratio, which is a very good thing in most of the cases. So the cast iron is iron alloys containing 2.1 to 4% of the carbon and from 1% to 3% of the silicon, which is actually the sand. And that's why if you are going to break a part of the stainless steel, you will see actually the crystalline shape due to the presence of the silicon in it. Now, if you remember what was the percentage of the carbon in the plain carbon, what was the percentage in that case? It was something between 0.02 to 2.11. Now you can see that the content of the carbon in the cast iron is going to be from 2.1 up to 4%. This composition is going to make them highly suitable for the casting of the metals, and the tonnage of the cast iron casting in several times that of all the other cast metal parts combined, and excluding the cast ingots in the steel making that are going to be subsequently rolled into parts, plates, and the similar stocks. The overall tonnage of the cast iron is going to be only seconds to the steel among the metals. The types of the cast iron we can have are the gray cast iron, the ductile cast iron, the white cast iron, the malleable cast iron, and other various alloys of the cast irons. When you are going to start the engine block, you're going to start with the engine block assignment, right? So in the engine block assignment, you have to choose what the material you're going to use for the engine block to cast with. So actually we're talking about the gray cast iron, and you have to specify why you are going to choose this material. The other metals are the non-ferrous metal, which does not contain iron with them. So although are not going to be strong as the steel, but certain non-ferrous alloys have the strength to weight ratio that make them competitive with the steel in some application. Now, what is the main application you can say about the non-ferrous metal due to the strength to weight ratio? What are the airplanes are made from? Aluminium or? Titanium is too expensive. That's for the spaceship they're using titanium. You can use chromium. Okay. which are non-ferrous materials which have a very high strength to weight ratio. So many non-ferrous metals have the properties other than the mechanical that make them ideal for the application which steel would not be suitable to. Now the aluminum is the first one. It's a light metal. It's often specified in engineering application for this feature. Because it's light, you always try to choose the aluminum as the first option. It's also at the same time have very high electrical and thermal conductivity. Its corrosion resistance due to the formation of the hard-tin oxide surface film. And it's very ductile metals and noted for the formability. It's low in strength when it's going to be pure, but it simply can be alloyed and heat treated to compete with some steels, especially when it's going to be the weight is going to be taken in consideration. Now, actually, this very important thing, and even when we're going to work in the future, is about the oxidization layer we're going to have at the top of the top surface of the aluminum. So usually, if you try to scratch any aluminum surface, you will come back to it after 2 days. You will see that the color has been changed to be the same as the old color. It's oxidized very fast, but simply we don't want to oxidize it further. So usually when they do the casting for the aluminum, they try to keep the oxidized layer on the top. They just want to keep it. So we're not going to oxidize more layer of the metal when you do the casting. The other types is the manganese and magnesium and alloys. Is going to be the lightest of the structural metals, available in both wrought and the casted form, relatively easy to machine. In all processing of the magnesium, a small part oxidized rapidly present fire hazard, and this is the most important thing. So actually, when you do the machining, the small chips at high temperature may be flamed. As a pure metal, it's soft and lack of sufficient strength for most of the engineering application, but it needs to be alloyed and heat treated to achieve the strength comparable to the aluminum alloys. Strength to weight ratio is going to be advantage in the aircraft and missile components. The copper is one of the oldest metals known for the mankind. Low electrical resistivity, excellent thermal conductor, and corrosion resistance. Now, actually what's happened that we even have the age which called the Bronze Age, because they're using the copper. They actually the copper was very important in the early time of the manufacturing because it's melt at lower temperature. A country like Cyprus, you know where Cyprus is? If you take a look to Cyprus nowadays, you can see there are some few trees around the island. But actually, the historian says that Cyprus was a jungle, but they found the copper there. So they were getting the ore, they tried to melt it, cast it, and export it as ingots. And that's why they cut all the trees at that time. So actually the wood temperature, the wood fire temperature was enough to melt the copper, but they destroyed the island. Actually, we keep doing the same thing on Earth. So the strength and the hardness of the copper is relatively going to be low. To improve this strength, copper is frequently alloyed with, to make the bronze, we are going to to alloy the copper with the tin, which is once again a low melting temperature metal. It's widely used. We can use as a brass, where the alloy of the copper and the zinc. And the high strength of the alloy is going to be the beryllium copper, and which can be heat treated and going to have a high strength and used for the spring manufacturing. The nickel and its alloys, similar to the iron, where the modulus of elasticity is going to be as much as for the iron and the steel, something about 270 gigapascal. And it has a good magnetic properties like the iron. But different from the steel, for more corrosion resistance and have high temperature properties of the nickel are going to be superior. Alloys of the nickel are commercially important and noted for the corrosion resistance and high temperature performance. In addition, the number of the super alloy are all based on the nickel. The titanium and its alloy, it's very precious metal, only 1% of the Earth's crust, while the aluminum is something about 8%. Density of the titanium is between the aluminum and the iron, which make it lightweight and good for the strength to weight ratio. So it's hard to have good lightweight and good strength to weight ratio. You said you can use it for the airplane, but actually because it's expensive, it's very limited application in the airplane, but they can use it for the spaceships. Lower coefficient of the thermal expansion among the metals and retain good strength at elevated temperatures. At room temperature, the titanium form a thin adherent oxide coating to provide an excellent corrosion resistance. The titanium alloys are used in the high strength components at temperature ranging up to above 550 centigrade, especially when the excellent strength to weight ratio is going to be exploited. Alloying elements are used with the titanium are the aluminum, the manganese, tin, and the vanadium. The pure titanium is reactive, and this is one of the limitations we have in manufacturing. The zinc and its alloy is a low melting point, make it attractive in the casting of the metals, especially in the die casting process. It also provides a good corrosion protection when it's going to be coated with onto the steel or the iron. And the term galvanized steels refers to a steel coated with the zinc, widely used as an alloy with the copper to make the brass. The super alloy is a high performance alloy designed to meet the demanding of the requirement for the strength and the resistance to the surface degradations at high surface temperatures. And that's why most of the power plants or the nuclear plants, they're usually using the super alloy for their components, even the piping and the valves. Many super alloys contain substantial amount of the 3 or more metals rather than the consisting of the one base metal and alloying elements like what we have in the other alloys process. Commercially important because they are very expensive, and technology important because of the unique properties. High temperature performance is excellent, tensile strength, hold hardness, creep resistance, and corrosion resistance at very elevated temperatures, which can be up to 1,100 centigrade. So we're talking about power plant where the temperature is going to be normally above 1,000 degrees. The application are the gas turbine, jet and the rocket engines, the steam turbines, and the nuclear power plants. We have 3 groups of the super alloys. The iron-based alloy, where the base one is going to be the iron, but it's going to be less than 50%, alloyed with the nickel, chromium, and the carbon. We also have the nickel-based alloys, where better high temperature strength than the alloy steel, alloyed with the chromium, carbon, ferrite, and titanium. The cobalt-based alloys, where it's going to contain 40% cobalt and 20% chromium. And virtually super alloy strength by the participation of the hardening process. Now, for the ceramic, is an inorganic compound consisting of the metals or semi-metals materials and one or more non-metals. The important examples of the non-metals are the silica, the alumina, and the hydrous aluminum silicates. It have a good high hardness. That's why it can be used for the surface finishing. Especially you can find now in most of the phone, they usually tell you that the back is coated with the ceramic. Also, it have good electrical and thermal insulating and good chemical stability, and also have a high melting temperature. But it's brittle and have no ductility, and can cause a problem in both the processing and performance of the ceramic products. Some ceramic are translucent, like the window glass, based on the silica, and being clearest example. 3 basic categories of the ceramics are the traditional ceramic, the new ceramic, and the glasses. The polymers, we said, is a long chain of the molecules of the mers. Each molecule is made up of the repeating units connected together. And they may be in thousands and even in millions of units in a single polymer molecules. And mold polymers are based on the carbon and are therefore considered to be an organic chemicals. As engineering materials, it's appropriate to divide them into the following, as we mentioned earlier: the thermoplastic polymers, the thermosetting polymers, and the elastomers. Now, can you give me once again an example of the thermoplastic polymers? Acrylic. And how you can simply test if the plastic you have is thermoplastic or thermosetting? By increasing the temperature. Don't try that at home, by the way. Increasing the temperature make the thing melt. Okay, that means it's thermoplastic. But something like the epoxy and other type of the adhesive which has been taken from the carbon, like actually from plastic, actually when they're going to be solidified, the heat is not going to be melt them. So they're going to be a thermosetting. And the third type is the elastomers, which is going to have more elasticity rather than the plasticity, and the rubber is a common example for that. Okay, so that's it for today, and I hope, yeah, well, actually, we're still at week 2, short lectures, but after that it's going to be long lectures. Okay, so any questions? Good. Enjoy your lunch.